All right, welcome back, everybody. So this is section 11.6, day 1. Now let's talk about where we're headed, okay? The Algebra 1 teachers, we've all planned out through the end of the year. Obviously, there's only 17 more classes to plan. So here's what we're going to be doing. Here's the next step here. We're doing section 11.6 today and tomorrow. Section 11.7 Monday. Review Tuesday, Wednesday. And we're going to quiz next Thursday over just those two sections. And then we'll do section 11.8 and 11.9. That'll be the following week. So we're looking at, obviously next week again is a late start. We got some late start days next week as well, the 4th and the 5th, because it's the science test, but you guys don't take science tests. So 11.6, 11.6, or sorry, 11.6, 11.6, 11.7, review, quiz next week from today. And then we have 11.8 and 11.9, and we're going to review and we're going to test by the 14th. And then you know what we do? Exam review. So we really only have a quiz and a test. Quiz next Friday, quiz next Thursday, and then our test is going to be that following Friday after that. And then again, you'll have some time to work on your exam review, and then we'll go over our exam review the rest of that week. Okay, so we've got really 4 more sections to learn: 11.6, 11.7, 11.8, 11.9. The countdown has begun. So for a warm-up for you guys today, I would like you to write out the first 12 perfect squares. You're going to need to do this for our work today. Go ahead and list out the first 12 perfect squares. What is a perfect square? A perfect square is a number that you multiply by itself. So like, for example, 1 squared, 1 times 1 is 1. So 1, I just gave you the first number on your list, 1. And then you do 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 12. In a perfect world, you do this from memory. Yeah. I went to every game. You watching this thing? No. Okay. Start this off. First 12. Everything is up there. Oh, that's what.
I gotta look at it and figure out which one that came.
Yep. Yes, I did. I said 2 squares is 4. Yeah, that's 4. Perfect squares are the actual numbers.
Also,
Okay, so let's talk about our first 12 perfect squares. Well, the first couple should be pretty easy and pretty recognizable. Like if I take 1 squared, that's obviously 1. 2 squared, 4. What's 3 squared? What's 4 squared? 5 squared? 6 squared. Now, were we able to do those at least from memory? Those are pretty recognizable. I hope up to 10 is recognizable. Let's keep going. What's 7 squared? 8 squared? 9 squared? 10 squared. I think you should know those. I think those, with no question, you should have those in your brain. Yeah. I'm never going to test you on that, but that going forward, moving forward, you should really have all of those perfect squares memorized in your brain. Now, my Algebra 1 teacher, we took a timed test. We had to go up to 20. We had to memorize up to 20. We had 20 seconds. Oops, I just got 12, but 11 squared is 121, and 12 squared is 144. My Algebra 1 teacher, we had 20, 30 seconds, and you had to write out the first 20 perfect squares. And that was it. You had to turn your paper over, put your pencil down at the end of 30 seconds. You had to know those. You just had to have them memorized. You couldn't work it out. You had to have them memorized. What's the benefit of that? The benefit of that is you recognizing those numbers. Those are going to be key numbers that you're going to see, especially when we start working with square roots, which is what we're going to be looking at in sections 11.6 and 11.7. Radical expressions. Okay? Because what we're looking at here is if we square those numbers, we get to the number on the right side, right? 2 squared is 4. 3 squared is 9. 4 squared is 16. But how do we go backward? How do we go backward? How do we take 81 and make it 9? Well, we take the square root of that number, right? The square root of 81 is 9. The square root of 49 is 7. The square root of 144 is 12. So that's really what we're going to be working with in this lesson here today. Taking those perfect squares and reducing them down, and maybe what happens if they're not perfect squares. All right, so again, 2 days on section 11.6. Let's first start by defining what we have as a radical expression. A radical expression is any expression that contains a radical sign. Now, we normally think of a square root. A square root. And that's really all we're going to be dealing with today. Just square roots. I actually don't know. I don't think we get to anything other than square roots. But what you could have is what's called a third root. Or you could have something called a fourth root. Those are all radical expressions that denote something a little different. You know how you're looking for two numbers that multiply by itself? Basically, you're looking for a buddy. Like 3 times 3 is 9, therefore 9 is a perfect square, therefore the square root of 9 is 3. If I were taking the third root or fourth root of a number, you'd be trying to find a number that multiplies by itself 3 or 4 times to get that bigger number. All of those are considered radical expressions. We're mostly going to be working with this square root thing. Now, you can put a 2 right in that little pocket to denote a square root, but it's the same thing as like, if it's not written, you assume that it's a 2. If you do not see a number in that little crease, you assume that it's a square root. Just like if there's a variable, you just have x. What do you assume the power is on x? 1. You assume that even though it's not written there, right? That's the same type of thing. If you see a radical sign and there's no number written in that little pocket, then you just assume that it's a square root. These are examples of radical expressions like the square root of 14. Basically, if you have the square root of any numerator, then there's a radical expression. If I ever refer to the thing called the radicand, a radicand is the thing that's underneath the radical. Anytime I talk about a radicand, that's the thing that you are square rooting. Like 14, like L squared plus W squared, like 2GD, like D. like 2, like 18. Those are called radicands. The thing underneath the radical is called a radicand. Okay? It may contain one term, it may contain multiple terms, whatever. We know that the square root of 16 is 4 because 4 squared equals 16. That's what I've been talking about here. So we could say 16 is what's called a perfect square. The square root of a perfect number is another whole number, right? The square root of a perfect square is a whole number. If it's not a perfect square and we go to try to take the square root, it's not a whole number. Like if you try to punch in the square root of 10 in your calculator, you get some messy decimal. You get an irrational number. If you take the square root of 16 in your calculator, it comes out nice, clean, 4. Okay? Now, my opinion is that these should be memorized, right? I've said that before during this period. My opinion is that 1 through 10, square roots 1 through 100 should be memorized. You should have those in your brain. Am I going to do a time test for you? No. But it might also be good to start recognizing 11 through 20. So let's go ahead and fill out the rest of that chart. No? Oh, there it is. Let's go ahead and fill out the rest of that chart through 20. Like we saw on our warm-up, what's 11 squared? 121. So the square root of 121 is 11. What was 12 squared? 144. 13 squared is 169. You know what's cool about 13 and 14? They're swapped. If you take 14, that's 196. 13 squared is 169. 14 squared is 196. Those two last numbers are swapped. 15 squared, 225. 16, 256. 17 squared, 324. 324. 360. I was going to try to do it in my head, and then this is 1. Again, my Algebra 1 teacher had us 30 seconds. 30 seconds, you got to write them all down, 1 through 20. No, I'm not that mean. He was a mean old man. I may be old enough. I think you should start recognizing those numbers. Like if you see a 289, that's 17 squared. That might be helpful later on. Usually, do you have your calculator that you could quickly take the square root of the number to see if it actually is 17? Yes. But you should have that in your brain. You should start to recognize perfect squares like that. Okay? Because again, it will help you in the long run. Now, what will happen if it's not a perfect square underneath the radical? What will happen if it's something messy underneath the radical? Let's take a look. If I tell you to put something in simplest form, these are the conditions for simplest form. The first thing is that the radicand has no perfect square factor. And you're going to see what I mean here in a second. You cannot have a perfect square factor included in the radicand. Also, the radicand cannot contain any fractions. If you've got a square root of a fraction, no good. You got to simplify it. And I'll show you how to in a minute. Another thing, there are no square roots in any denominator. In that case, we will have to do something called rationalizing the denominator, which is a little funky, but again, we'll get there. We'll talk through it. The following examples have not been simplified completely. Why not? Well, take a look at the square root of 8. I said it can't have any perfect square factors. Aren't the factors of 8, 4, and 2? Isn't 4 a perfect square? So that is not technically simplified. The square root of 2/5, not technically simplified. I've got to take the square root of a fraction. I've got to do something with it. And also 24 divided by the square root of 2. I've got a square root in the denominator. Not simplified. So when I ask for simplest radical form, you're going to hear me talk about simplest radical form. I'm going to say that phrase a lot. That means that you've got to reduce all radicals appropriately. Remember that a positive number has 2 square roots, one positive, one negative. However, That square root indicates the non-negative square root. You know how we were always talking about the plus or minus in front of the square root? If I give you the square root, you don't have to worry about the plus or minus. Right? If I give you the square root, you don't have to worry about the plus or minus. Okay? All right. Let's take a look here. Simplify each. This may look difficult right off the bat. First off, why is it not simplified? Because it's a fraction. Simple, because it's a fraction. So is there a way to reduce down this fraction? What is 2/50th? 1/25th. And now look at what I can do. If you've got the square root of a fraction, you can take the square root of the top and then the square root of the bottom. What is the square root of 1? What's the square root of 25? So that reduces down all the way to 1/5. It's in simplest form because the radical has gone away. I've used the operation of the radical. Remember that's really what it is. The operation is the radical. That's an operation in and of itself. It's taking what number do I multiply by itself to get that thing? Take a look at another one. Let's reduce this expression on the inside. What do I get if I reduce that expression? What do I get if I actually take 4 squared plus 3 squared? What's that? 25. I get 25. 4 squared is 16. 3 squared is 9. So I get the square root of 25, which is 5. You might be tempted to say 7. I always have a lot of people trying to say 7. Where am I getting the 7? The 4 and the 3. A lot of people try to take off the radical and say, oh, it'll cancel out with those squares. No, that doesn't work like that. If you've got a sum underneath, if you've got addition underneath the radical, you cannot square root that. Look at that, you have a little pencil. That was an off there too. No, that doesn't always happen. Documentation of your does. So if you've got a sum underneath, you have to reduce that sum and then take the square root. Let's take a look at this one. Now, this is going to come into play soon. I'm kind of getting you ready for something else. You notice how we have that binomial, that 2-term, squared? If you have a square and a squared, square root and a squared, like this, I've taken the square root of something squared. Those are inverses of one another, so they will cancel out. If you ever have something, if you're taking the square root of something squared, like if you're taking the square root of just x squared, the square root of x squared cancels. The square root of x plus 5 squared cancels. So you're just left with an x plus 5. We're going to use this property a little bit later on. All right, now let's work on reducing some radicals. I'm going to teach you a method of reducing radicals that I like to call the buddy system. I'm going to teach you a way to reduce radicals by the buddy system. And what we're going to do is create a factor tree. We've already done this year. We should know how to create factor trees. Let's create a factor tree out of 60. Well, 60, 2 times 30, 30, 2 times 15, 15 is 3 times 5. Everybody follow me there? We've done that many times this year already. So what I have here is the square root of 2 times 2 times 3 times 5. Now, in square root land, in the square root house, it's like date night in the square root house. You got to have a date. You got to have a buddy to leave the house. And your buddy has to match. So do you see how the 2 has a buddy? It gets to leave the house. Okay? The 2s have the buddy. They get to leave the house. 1, 2 on the outside. When they leave the house, they become 1. It's like marriage. The 2 become 1. Why is that the case? Why, mathematically, why is that the case? Because aren't I taking inside the radical 2 squared? Isn't that truly like a 4? And what is the square root of 4? 2. So that's why it just becomes one of those things on the outside. Okay? I like to remember it in that fun little story thing where, you know, you got a buddy, you get a match, you get to leave the house and you become one. Now this is where it gets to starts to get a little. No, it's not. This is where the story takes a little bit of a turn. And this is weird. So in my storyline here, what happens to the things on the inside? They stay in the house and multiply? No, whoa, this is not health class, this is math class. Whoa. They stay in the house and multiply? Yeah. So that's a 15 back together. So 2 radical 15.
Is that our final answer?
That's your final answer. How do you know that's a final answer? Well, because 15, if I break down 15, does it have any buddies? No, it's just 3 and 5. The 3 and 5 have no buddies to go outside the house with. Yeah.
And then isn't 15 the second power?
No. I'm not taking it to the second power. Like if you square rooted 15, does it come out nice and even? No. That means that it's done. You leave it as that simplest radical form. So let's do that process over again. Let's take the square root of 72. All right, let's break it down. 2 times what? And then 36 is 2 times 18. 18 is 2 times 9. 9 is 3 times 3. Y'all follow me there? So yeah, there's a good amount of them here. So what do we do here? Well, I've got 2 times 2 times 2 times 3 times 3. You got to have a buddy to leave the house, right? Rosalie. I'll talk about that in a second. Well, remind me to come back to that. Circle back. So, got to have a buddy to leave the house. Buddy, sorry, my leftover too, lonely. What else gets to leave the house? 3. The story gets even weirder now because they have to multiply outside the house. So 2 times 3 on the outside and then a 2 on the inside, right? The 2 and the 3 circled in red come on the outside as 1. And then this lonely 2 stays on the inside. But yeah, again, my story is even weirder now. 2 times 3 on the outside, multiply on outside the house? Okay. Get a new story. 6 radical 2. Now, Rosalie brought up a really good point. She said, well, what about, isn't 72 just 2 times 36? And what is the square root of 36? Yeah, so wouldn't this just be 6 times the square root of 2? Yes, you can do that. If you recognize that, you can do that. If you see a perfect square in there, that's why 60 was essentially just 16 times, no, not 16, excuse me, 4 times 15. And 4 was our perfect square. That's the biggest perfect square that divides 16 evenly. So we could have just taken it 2 times the square root of 15. So if that works, you can do it that way. Let's take another one here. Now, 675. Do we easily see something that could be maybe a 25? But let's reduce it down. Oh, I see. Yeah. Totally. Yeah. And then 675. Okay. Well, 675. I see that I could divide by 5. So 5 times 135, and then that ends in a 5 as well, so I'm going to divide that by 5. So it's 5 times 27. And then that's 3 times 9, and then 3 times 3. Okay. Buddy system. I like to go in order. 3 times 3 times 3 times 5 times 5. Buddies. Okay. A 3 and a 5 come out. And then that lonely 3 that doesn't have anybody to go outside the house with. So that means I've got 3 times 5 is 15 radical 3.
Wait, so if I did like the 3 and then the 225, I would just put 15 on the outside and the 3 on the inside.
Yeah, then that's exactly it. Yeah, that's true. So you recognize the 225 times 3? And 225 is a big perfect square, which is 15. 15 on the outside, 3 on the inside. Yep.
The first square root, could we do 5 times 5 times 3 times 3 times 3?
Yeah, that's fine, just as long as you get the same answer. I like to put them in order, because, I don't know. Now, what happens when there's a number on the outside of the house? You leave it until the very end. Does that get included with our 96? No. 96 is inside the house. I've got to reduce down things inside the house. So, square root of 96. Well, 96 divided by 2 is 48. 2 times 48, and then 2 times 24, and then 2 times 12, and 2 times 6, and 2 times 3. Oop. Break it in half each time. So what does that mean? That means I got a 3 on the outside. Don't let that go. And then I got 1, 2, 3, 4, 5 twos. 2, 3, 4, 5 twos. And then a 3. All right, buddies. Buddy. So on the outside, I had a 3 from the original problem. And then 2 twos come out. And then what's left over on the inside? Which make a 6. Don't say 5. Makes a 6. Remember, we're multiplying here. And then on the outside, I've got a 3 times 2 times 2. 3 times 2 times 2. That gets me a 12. Let me just double check. There was none of this. No square roots like this on your test, right? On your OST, right? There's usually never those on there, so I just wanted to make sure. All right, so what do we do with the variable then? That's what we're looking at next. What do we do with a variable? Well, we assume all variables represent non-negative numbers because that's square root negative. Do you have a question? No, because you would only be reducing to 6, which is only a 2 and a 3. Yeah.
Where did the 6 come from?
Let me jump back here. The 6 came from right here.
Okay.
Whatever's left over multiplies back together.
So you have the pairs and then you have whatever's left.
Yeah. So you got to separate the things that can come out, things that have to stay in. Okay, so what happens if we have the square root of x squared? We just talked about that a little bit ago. If you take the square root of x squared, what do you get? Aren't those inverses of one another? You just get x, right? Those will cancel each other out. Why is that the case? Why do they just cancel out? Because isn't x squared x times x? And okay, buddy. X comes out. Is there anything left over on the inside? No, it just goes away. If everything comes out, the square root just goes away. Well, what happens if I take that x to the third? Well, let's write it out. X times x times x. Buddy, with 1 staying on the inside. Okay. What about x to the fourth then? How does this change if I take an x to the fourth? Well, buddies, x squared on the outside, right? Don't say 2x, not adding x plus x, it's x times x, which is x squared. Okay, what if I just keep going? 1, 2, 3, 4, 5. All right, buddy. So I've got 2 on the outside and 1 on the inside. Let's do one more. X to the 6th. 2, 3, 4, 5, 6. Buddies. Oh, that's too far. 2, 3, 4, 5, 6. Buddies. 3 of them coming out. X to the 3rd. Does anybody see a pattern?
Yes.
What happened? Divides it by 2. It divides it by 2. Look at the power. Aren't I dividing by 2? Is that ring true for all my simplest one? Yeah. My power was 2, I divided by 2, I get 1. My power was 4, I divided by 2, I get 2. My power is 6, I divided by 2, I get 3. So let me ask you this. What is x to the 18th power, the square root of that? X to the 9th. Now, why is this thing happening with an odd one? Well, what you do is basically you're still dividing by 2, but what's the remainder left over? Like, think about 5. If I take 5 divided by 2, I get 2 with the remainder 1. 2 coming out, 1 remaining on the inside. Okay? So it still works. It's just easier to do with even powers. So what would happen if I have this? Well, how many x's are going to be on the outside? 2. How many y's are going to be on the outside? Are there any x's or y's left over on the inside? No, because they're even powers. Now, is there a z coming out? Yeah. Because I have 1 z out and 1 staying in. Why is that the case? Yes, but 1 came out, so it removed 2 of them with 1 left over. But 3 divided by 2 is 1 remainder 1, right? 1 on the outside, remaining 1 on the inside. Okay. Could I have just listed them all out like I just did in the last problem? Of course. It would have taken me a minute, but it's easier to use the rule about just dividing by 2. Perfect. 10 minutes left, one more example. We got 50x squared y to the 3rd. Now, if I put those two things together, numbers and letters, we just do that same process with the numbers and the letters. So let's prime factorization. 2 times 25, 5 times 5. Now let's write it all out. Heck, if we wanted to, 2 times 5 times 5, let's just go for it. X times x, y times y times y. I know you probably don't need to do that, but why not? It's fun. Lots of buddies. So what comes out? What should sit on the outside? Just one of them. 5xy. 5xy. And what should go on the inside? 2y. And that's in simplest radical form. Try another one. Okay, 160. Okay. That's 2 times 80. 2 times 40. 2 times 20. 2 times 10. 2 times 5. A lot of 2's in there, right? So prime factorization looks like this. Square root of 1, 2, 3, 4, 5 2's. 1, 2, 3, 4, 5 2's. And then a 5. 4 a's. 1, 2, 3, 4. I don't really need to do that part. And 2 b's. Because I could use the rule about dividing by 2 with the variables. Buddies, 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 buddies. All right, so we've got what number should go on the outside? 4. 2 times 2 should be a 4 on the outside. A to the 2nd, B. What number should be on the inside? 10. Any letters? No. Let's do one more. Just be careful of the number sitting on the outside. You'd be surprised. More often than not, people just kind of like let that go. Like that 5 just kind of like vanishes into thin air. So we've got 5, and then let's break down the 504. 2 times, what would that be? 504 divided by 2. It's 252. Divided by 2.
Can I borrow David for just 2
Sure.
seconds?
Yeah, go for it.
David.
Pause, right? Now shrub back. Yeah. Point at 2 again. 2 and 126. And then 2 and 63. 63, wasn't that 7 times 9? And then 3 and 3. See, the difficulty may come with, reducing down those numbers. I don't know. Maybe some of you find that difficult, but I'm not. So this gives me a 5 that's already on the outside. Square root of 1, 2, 3 2's. 1, 2, 3 2's. A 7, and then 2 3's. And then we have x and x, and then y. Here we go. Buddy, buddy, buddy. So that gives me what number goes on the outside? A 6. But don't forget about the 5 times 6 on the outside. See, did we already forget about it? And then on the inside, and then an x. And then on the inside, a 14y. 2 and the 7 make a 14. The y was lonely. So on the outside, that should be a 30x. Square root of 14y. How do we feel about that? Good. Let me hand you guys 9. That's like 9 problems for tonight? I should add some. You want me to add some homework?
No.
I feel like 9 is good. It's not enough. We need more than 9 problems, don't we?
I feel like our school will keep the right.
Go down like 3 more miles.
What is this supposed to be excited?
I heard you did studying with an apple.
Yeah, moving on up.
It's relaxed. You've been doing it for months. Relax.
By the time you decide to do 100 subscribers, plus we're gonna end up being at 200.
I'm at 117 right now, I think. If I go back under 100, you're not getting it.
I'll go first.
I'm gonna do a day in the life of that. I'm gonna record myself all day. We'll do a time lapse.
Wait,
Should I do a time lapse the next class?
Yeah.
Wait, you really should. That'd be kind of cool.
I'll set it right. Oh, I'm recording still.
But if it's then,
So long, everybody. You kind of get a day in the life anyway because they're recording.